All right, so something we look at is that we say that any response, all right, any of the responses, let's see, like here, for example, in this example, you see this one is with damping. So you see that because of the damping, the amplitude of the response decreases every single time, no? So there is a way to determine what is the value of the damping from actually the time response, okay? And that's generally the way it's done. Let's say you have a structure and you want to find what is the damping of that structure. What is the easiest way? Is by experimental procedure. So you can go in an experimental procedure, you can put an accelerometer, no? You can read what is the deformation of that system you're trying to study, and then from the time response, maybe you can deduct what is the damping of that structure. Okay? So I'm going to just show you how that is done. It's very easy, and it's called the logarithmic decrement. Okay, so let's put over here the logarithmic decrement represents the rate at which the amplitude of the free damp vibration response decreases. Okay, so basically if I do the figure, okay, so what do they call the logarithmic decrement? Because the idea already on the figure, you could put this amplitude here within those functions. And let's say the response could be something like this. Okay, and so on. So it would be okay, and here this is really the time. I just put it because that's the way it is on the for the units. Okay, so we already have this figure. So here, this will be the amplitude at this time step, x1. It will be the amplitude at this time step x2. So it will be t1, t2. So this will be the period. The damping period will be equal to 2 pi divided by omega sub d. And I think I already said on the last figure, this line over here is the magnitude of the amplitude as given by the amplitude of the exponential of negative of the damping ratio natural frequency times t. Okay, so something I didn't put over here, but obviously we studied 3 cases. Now, when we studied the response was the overdamp, critically damp, and underdamp, no? Okay, and you had the overdamp and critically damp, the response was basically going straight to 0. Okay, so this is only true for the underdamp case. All right, so let's say here we're calling the solution for the underdamp free vibration. So the equation was x of t equal to the amplitude exponential of minus c omega and t times sine omega sub dt minus phi, where the damp natural frequency was given by square root of 1 minus c squared omega sub n. Okay, so the procedure is pretty easy. What do we need to find out is that what is the difference between the ratio of x1 and x2? Okay, so basically that's what we are doing. So x1, ratio of x1 over x2. So it's equal to the ratio of x at t equal to 1 or x at t equal to 2. So by looking at the solution, this is equal to the amplitude of exponential of minus c omega sub n t sub 1 sine omega sub d t sub 1 minus phi. Divided by the amplitude of exponential of minus c omega sub n t sub 2 sine omega sub d t sub 2 minus phi. Okay, so let's put here, knowing that T2 is actually equal to what? T2 will be equal to T1 plus whatever time is needed to go from this point to this point, no? Which is the period. So tau sub d where tau sub d we know is equal to 2 pi from the figure, okay, divided by omega sub d. And then so we can rewrite this term over here, sine of omega sub d t sub 2 minus phi, as sine of 2 pi plus omega sub d t sub 1 minus phi Why am I putting 2 pi? Because 2 pi represents once you go 1 period around the circle, no? Yeah, 360 degrees. And remember, when you go from this point to this point, it means that you go once around the circle. Yeah? So T2 will be here, you're here, you go once around the circle, you end up over here. All right. And this, if you add 2 pi to the response, basically what you get is sine. This is one of the properties of the sine omega sub d t sub 1 minus phi. So you can rewrite this one as just T1. Basically, it makes sense. If you ask 2 pi, the only thing you're doing is go back to the same location, no? Okay. So sine omega d t sub 2 minus phi is actually equal to sine omega t sub 1 minus phi. Because after one cycle, here after one cycle, you just end up at the same location around the circle. I mean, really the circle is going to be, really should be a circle that will go here, and then on the second one, it will be with lower amplitude, no? Okay, but it's still going to go once to the circle. Okay, so now if I substitute this expression here into this one over here, you see that the sine omega d t sub 1 minus phi is going to cancel out, and the amplitudes are also going to cancel out. Okay, so maybe I have space to put it over here. So with all this stuff, we can rewrite that x1 over x2 will be equal to exponential of minus c omega sub n t sub 1 divided by exponential minus c omega sub n t sub 2 or exponential of minus c omega sub n t sub 1 divided by exponential of minus c omega sub n T1 plus pi sub d, and this will be equal to exponential c sub n pi sub d. Okay, so let me call this one Roman 1 because that way I don't have to write it. So this is just basic algebra. All right, so almost done. So solving. That equation over here that I'm just going to rewrite, but just the first term, so which is x1 over x2 equal to exponential of c omega sub n pi sub d. Okay, how do you solve this equation for the damping? You need to take the log function, no? Okay, so let's say the damping, we call here delta, will be equal to the log of x1 over x2. So you take the log of the exponential function, this would be equal just to c omega sub n pi sub d. And if you remember, the pi sub d is equal to 2 pi divided by omega sub d. So basically this, we can write this as omega sub n divided by omega sub d times 2 pi. And we know that the damping ratio, the damp natural frequency is equal to the square root of 1 minus c squared omega sub n. So that means that we're going to have take the square root over here, omega sub n times 2 pi. So that finally you have that the decrease in amplitude will be equal to 2 pi c divided by 1 minus c squared. Okay, so remember that here delta is what? Delta is just the ratio of x1 over x2, no? So it's the decrement in amplitude, so decrement ratio, okay, to make it simple. Okay, so now what we need to find here is what? Is the damping ratio C. So what do we need to do? Experimentally, if we have this function, all we need to do is to measure x1 and x2, no? Yeah? And then we could solve this equation for the damping ratio, all right? So this is what we need to do. Okay, so again, this is the ratio. What's important is the ratio, but yes, the delta is actually the log of the ratio of the decrement, okay? So basically what I need to do now is that to determine the damping ratio, XC, it suffices to measure any two consecutive deformations x1 and x2 in one cycle. Maybe I'm gonna add that, okay? The importance during the one cycle, during one period. So solving this equation, so solving the equation for the damping ratio. I mean, I have the derivation, but I don't think I need to give you the derivation for absolutely everything, okay? This is not the important part, is that you understand the process. So if you solve this equation, you can go to Maple or MATLAB if you want. It's not difficult to solve, or you can do it by hand. You find that the damping ratio, the solution, is given by pi squared plus delta squared Okay, and Jali, I'll put it on this page for small. What happens if you have something small and you square something small? It basically goes to zero, no? So for small damping, you can actually find that this equation simplifies to, so this will be basically zero, and this will be just the deformation, and this will be 2 pi, okay? And that's Jali. The damping Jali is small because if it's large, what's going to happen? If it's large Jali, this response is going to go very quick to zero, no? Okay. All right. All right, so we're going to look now at equivalent springs. Okay, so first one, we're going to look at springs in parallel. So again, you don't need to memorize these equations if you understand how things work, okay? So let's say you need to do a figure. So springs in parallel. You don't know what is a spring in parallel, so you just plot two springs in parallel, K1 and K2. Let's say that would be attached to a mass over here. Okay, and what I'm trying to do is what? To simplify this, in one spring that will be the equivalent spring. So here let's say we have a force. Okay, so this will be force of the spring 1. This will be the force of the spring 2. Okay, and this would be the force of the F equivalent spring. So in order to find what is equivalent, you need to find what would be this, I mean, in this case, something that you can relate. So can you relate over here? Can you say that the force of the equivalent spring needs to be equal to the force of the force spring by spring 1 plus the force of spring 2? Yeah, that makes sense, no? Okay. And now, what is the general definition of the force of a spring? Is force of a spring is equal to kx. All right. So now you can just rewrite this equation here as k1 x, because these two springs are going to move the same distance, no? Plus k2 x so this should be equal to what? K1 plus K2x. So that means that F equivalent is equal to this. And what would this be then? This will be your K equivalent. Okay, or F equivalent would be equal to K equivalent X. So generalizing the result, we have what? K equivalent will be equal to the summation of all the springs. But again, you don't need to memorize this. Is this that difficult to understand? Okay. And to tell you the truth, this works even though it's the contrary. Like when you had electrical engineering, then you need to find what is the equivalent resistance. No? You do the same thing. Okay, you don't need to memorize it. Okay, so we have springs in parallel. So now we're going to look at springs in series. And we do exactly the same thing. All right, so 2 springs in series. So again, here the strategy is exactly the same one. You need to do the figure. So without the figure, there's no way. So again, you're going to have here your force. This will be K1, K2. But now what you need to realize is that, so this one will be deforming X1, this one will be deforming X2, and you need to find the equivalent spring. So again, you need to find out stuff that you're able to relate. So in this case, with the force of spring 1 plus the force of spring 2 be equal to F? No, because both springs are subjected to the same force, no? So this time we cannot do what we did before with the forces. However, I mean, and look at the equation. This equation, what is the thing you need to relate? Either the force or the deformation, no? However, in this case, can you say that the total deformation will be X1 plus X2? Yes, no? The total deformation of the spring, how much this is going to move, needs to be equal to X1 plus X2. So we could just rewrite that X equivalent will be equal to X1 plus X2. And as before, you know the equation for a spring is F equal Kx, which will give you that X is F divided by K. So this will give you what? F divided by K1 plus F divided by K2. And this will be equal to the F divided by the K equivalent. Because the force is the same, no? The force experienced by the first spring is F, the force experienced by the second spring is F. Same thing for the equivalent. So over here, you see right away that you can cancel out the forces, and you have that 1 over K equivalent is equal of 1 over K1 plus 1 over K2. And again, we can say generalizing the result. We have that 1 over k equivalent will be equal to the summations 1 to n to the 1 over k sub n. All right. All right, so let's do a problem, not about this, but about something more general. Okay, so let's do this exercise. I'm gonna go a bit quick because I wanna make sure I finish it. And I want this to help you as an example for the homework. I'll make just half of this problem, but then that this is the type of problem I will probably give you on the first exam. I think first exam will be take home, okay? But there you have an idea, all right? So in this case, we have a pulley, a double pulley. So it's hard to sketch. Okay, so this is like one pulley that you glue to another one, no? So they are embedded. So both of them will have the same angular acceleration and angular velocity. But what's specific about this pulley is that they say, do you have a string that comes from the inner pulley that goes straight up? Then you have this one comes from here, but here there is a spring. Okay. And then out of the outer one, you have a damper. Okay, and all these will be attached to a fixed surface. All right, so let's say here we know that the radius of this one is r, and of the outside one is 2r. Okay, so let me give some data for r equal to 0.8 meters. The mass is 20 kilograms of the double pulley. The moment of inertia of this pulley about the center is given by m r squared divided by 2. The spring has a stiffness of 60 Newton meters, and the damping 24 newtons second square divided by meters. Okay, so in this problem, what we need to do is to determine the equation of motion in function of x, where x will be you could do it up or down, how much this is moving. and solve it. Okay? So again, I want to emphasize something. I'm being picky on the first homework because it's the only time we're going to do it. And it's probably going to, I told you already, it's probably going to be the hardest homework because to know how to solve differential equation is easy. Okay, I already showed you how to do it numerically. You can do it with MATLAB in 2 seconds. You can give any numerical equation, you're going to find the solution. But you need to make sure that you know that you're able to get the correct differential equation that represent whatever is happening on the system, no? And that is the difficult part. So that's why I'm trying to emphasize that in the first homework, okay? After that, the differential equation will be given to you. And this is the hard part, is to find the differential equation of motion, all right? So determine the equation of motion in function of x and solve it for the initial conditions okay, so the same as before. X of 0, this time we say start from 0, and the initial velocity v equal dx dt equal x dot at t equals 0 equals 0, okay? The simplest case you can have. All right, so there we go. So the way I solve these problems is always the same way. When I look at it, what type of motion is that pulley going to have? It's going to move in translation and rotation, no? Okay, so that means that in order to define the translation equation, we need to do the summation of force equals to ma. And in order to define the rotation equation, we're going to have to apply the moment equation, no? Okay, so the way I do that in my head is motion for this problem is translation plus rotation. Okay, so what does that put in my head is that I know I'm going to need here summation of forces equals to ma, and for this one, summation of moments equals to I alpha. So next I follow the procedure. Step 1, always to do some type of figure. Really, I should not call it free body diagram because free body means that it's not moving, but this is moving, but let's just call it for figure, okay? Figure body diagram, okay? Let's say that stands for instead of free body diagram. Okay, so the important part here is that you need one sketch for the left-hand side of the equation, one sketch for the right-hand side of the equation. So we do here okay. So let's see what we have. On this string over here, we're gonna have some tension T, okay? Then the spring here, what is the spring? This is gonna create a spring force. If you want, you can put, okay, F spring. And then on the damper here, we're gonna have F damper, F sub D. And then am I forgetting something? Yes, I'm forgetting the most important part. This will be mg. Okay, and then this will be moving how? You can do it up or down, it doesn't matter. So it will be MA, which is MX double dot. This is our X over here. So this is, we selected in that direction positive. And then we're gonna have here the I sub naught alpha. Okay. Okay, so over here, we write down the equation. So step 2, write dynamic, or what is the same thing, kinetic equations, which are what? The equation that defines the translation. Summation of forces equals to MA So here be careful because look at the figure. In this case, what did I selected for X positive will be going down, no? We can actually plot this up as well. But I mean, since I plotted down, let me change it. So what will you have? You will have mg will be positive minus T minus the force of the spring minus the force of the damper will be equal to what? MA, which is mx double dot. So let's say this will be your equation 1. Then the second equation that will define the rotation will be summation of moments about the center of the pulley. You need to specify the point. Okay, so point O will be equal to I sub O alpha. And you also need to specify what will be the positive direction for moments. So let's see, this will give you what? If you look at the figure. So what will be the moment created by the force T, by the force T? Would be T R, and this one would be positive or negative? Negative, okay. Then the one of the spring will be plus S spring times R, and then you will have plus F damper times 2R equal to the I sub naught, but we know the I sub naught is equal to what? R squared over 2. This is your I sub naught and alpha. So this would be your equation 2. Okay, so over here now, step 3, we need a lot more of equation because we don't know what S spring is, FD spring, and alpha. So we can go step 3. But I mean, it's very easy. I could have done it at the same time, but I just want to make sure that I follow the procedure. So I'm going to look at kinematics. So basically we have from the figure, this is F spring will be equal to some K, let's say X1, no? And the F damper will be equal to some coefficient C x dot 2 by definition. Remember, we said that the viscous damping is always proportional to the velocity. Okay. So in this case, the angle of deformation will be the same, no? Okay, so what could you say about x1? So this would be, if you want your additional equation, you could say that from figure, x1 is approximately or equal to what? Would be equal to r times what? R times theta. Okay, and that x2 similarly will be equal to what? Oh wait, no, here I did a mistake. Hold on one second. See, I was going too fast. So we're gonna do the same thing, but hold on one second. So in this case over here, okay, so we need to start from one point. So this will be 2. Okay, yeah. So where can we start over here? Is this point moving? What is the point that at that instant, when this is moving, imagine this is moving, no? But then you take a bunch of pictures. What is that, the point where everything is static at that point? What is the velocity and the velocity of this point? 0. So what will be the velocity of this point? 0, no? Okay, so we need to look at the motion. So from this point, what would be, let's say from this point here, let's call it A, what would be the motion of this point over here? It will look like this is, it will look like this pulley here is sliding from point A, no? Yes? This is like, I'm pretty sure you understand, but just imagine you have a football, okay? So when the football is rolling on the ground, it's not rotating from its center. It looks like it's rotating from its point of contact with the ground. Yeah? So here happens exactly the same thing. At this time, it would look like the pulley is rotating from this point. So from this point, what would be the deformation x1? Should be 2r, should be 2r theta, no? Yeah, it should be 2r, it should be twice. And what would be the one of C? It should be 3, no? Yeah. Be this one plus this one. Okay, so let's put that right away. So maybe let's eliminate this, and it's going to make it easier to do the other form. So at that instance, already here. So VA equals 0. Okay. So, and you know that, I think it's easier to do this one. Let me change the way I'm going to do it. So you know that velocity is equal to what? Distance over time, no? Okay, I'm going to make it, so for a time that is fixed, so let's say t equal 1, v will be equal to the distance. All right, so let's say, let me do another figure a bit bigger. So this will be point A, this will be point B, and this will be point C. Okay? And we know this is R and 2R. All right? So from point, what is the velocity of point B from point A? And this will be like going to dynamics. I'm going to give a lot more details than I should, but I don't think it's going to hurt. Velocity of B would be equal to the velocity of A plus omega cross R of B with respect to A. Do you remember this equation? Sort of. So the velocity of A, we know at that instant is 0. So again, I'm going to do it like if it was dynamic. So this should give you the cross product of I, JK of 0, 0, omega. And what is the position of B with respect to A? It is 2R 0, 0. Okay? So when you look at it, even the math will give you correct. This should give you what? Just a component on the y direction, no? Or an up and down, reaching the x. So this will give you here VB equals to 2R omega. Okay, and similarly, we could say that VC is exactly the same thing as VA plus omega cross R of C with respect to A. This is 0. So this will give you the same thing, I, J, K, 0, 0, omega. But this time, what will be the position of A with respect to C? Would be, no, would not be forward because from the inside. So it's from here. So let's see. So here 2R should be, oh, sorry, because I did here. Okay, if you look at the figure, this is, okay, this figure is incorrect. My fault. Where should be the point A? On the inside pulley, no? Okay, I didn't. So this is your inside pulley, this is your point A, but it doesn't change anything because the point we look at was point B, which will still be at 2R, no? Yeah. And now this one will be at what? It would be at 3R, no? Now here 3R, 0, 0. So this will give you that VC equal to 3R omega. Okay, and all these ones would be rotating with respect to omega, which is with respect to the center. Okay, so here, without going to into too much more detail, I mean, I could go more, but so for a fixed time, because again, imagine you just take photography. What could you say for this? You can just say that since the velocity is distance divided by time, the time is the same thing. This velocity should be, let's say, this one is going to do twice the distance, when this one is going to go 3 times the distance, no? Yes? So let's say we could just say that xp would be equal to twice the distance to x, and xc would be 3x. Is that clear, or do I need to give more detail? Okay, I could solve for the angle and equate, and it will give me the same thing. All right, so how much time I have? 10 minutes. Okay, so now what's going to happen? I can go and substitute over here into the two equations. So substituting into 1 and 2. What do you get? mg minus t minus 2kx minus 3cx dot equal to mx double dot. And the other one will be minus t times r minus 2k, no, plus 2kxr, this is the spring, plus 3c x dot to r equal to r squared over 2 alpha. So this is still equations 1 and 2, okay? So 1a, 2a, okay? So it's still the same. Okay, so the last one we need to obtain from kinematics is alpha. But again, this is going to be easy. So imagine you are in dynamics, so we can do the same thing over here again. We can find the acceleration of the center of the pulley, which would be point O over here. From point A would be equal acceleration of A plus alpha cross R of O with respect to A minus omega square R of O with respect to A. All right, we're going to do detail. I want to finish this. This term will cancel this one. And I'm going to ask you why. Maybe at the end. So it will be equal to I jk 0, 0 alpha. And position of O with respect to A will just be R. So this will give you that the acceleration of O, which is really our x double dot, will be equal to R alpha. Or you can just say that alpha will be equal to the x double dot over R. Okay, so substituting in to A, what do we get? Minus TR plus 2KRX plus 6CRX dot equal to MR over 2 X double dot. Okay, we're not gonna finish it today, but let me just write 2 more lines. So next, in step 4, let us solve the system of equations, which I'm just gonna write down. So it will be equation 1a. So mg minus t minus 2kx minus 3cx dot equal mx double dot, and minus t times r plus 2 krx plus 6crx dot equal mr over 2x double dot. So this is equation 1a to b. Okay, guys, so I think the homework is due for Thursday, no? Now, so work on it, but I think it's due Thursday probably at night, at midnight, like 11:59. So Thursday, my plan is to finish this problem and maybe look a little bit at homework. Okay, so we'll give you a bit of more or less what I'm looking for. But again, the first problem